Hello everyone. Today we are going to deal with electrostatics. But wait, what is electrostatics? When we divide this term into two parts, we get electro and statics. So electro is something related to electricity, which is something related to electric charges. So electric charges at rest, the static means at rest. So electric charges at rest is what electrostatics is. So whenever you come to a heavy term as in electrostatics, the simple meaning is electric charges at rest. Great. So before digging deeper into this chapter, we're going to deal with some basic concepts. Now what are the basic concepts? Frictional electricity, the number one. And then we're going to deal with conservation of charges and how the charges are always conserved. So let's go to frictional electricity. Now you know what? The beauty of science lies in the breaking of its words. You see any of the typical term of a science, just break it into parts, divide it and see to it that if you can get the meaning of every separate words. Now we are dealing with frictional electricity, so we'll break it into two parts, that is frictional and electricity, and we're going to understand it in a very beautiful manner. Now let's see frictional. You see, what is friction? It's an opposing force, right? Suppose I'm rubbing my two hands. So there is a kind of friction being developed here because of the contacts, because of the hills and dales which gets interlocked, right? So that is friction. And what is electricity? I know you know that, right? Electricity is simply electric charges in motion, not at rest, but in motion. So whenever the electrons, specifically to say, they start to move in a particular direction, say this one, electricity comes into play and we are surrounded by it, right? So simply the electricity which is generated through this friction is called as frictional electricity. That's amazing, isn't that? So now let's see how it happens. Suppose I'm rubbing with two hands. Suppose this is surface 1, this is surface 2, and I'm rubbing them, okay? I'm rubbing them, friction is being developed, frictional electricity is coming into play. Now just take into account that surface 1 has 2 electrons. Suppose, just take into account it has 2 electrons. And surface 2, that is surface 2, has 3 electrons, okay? Now when I'm rubbing, what is happening is, from surface, this one surface which has 2 electrons, 1 electron is being transferred. That is, it is donating its 1 electron to the second surface which has 3 electrons. So in starting, this surface was having 2 electrons and this 3 electrons, but when they are rubbed, that is when friction comes into play, it became 1 electron and it became 4 electrons, right? Everyone? So what happens? It loses electron. The proton is going to remain same because it's in the nucleus, as you all know that, right? So it loses electron. As it loses electron, the number of protons you see becomes more. They exceeds the electron, so it becomes positively charged. So my surface 1 being a donor becomes positively charged. On the other hand, my surface 2 being an acceptor, it gets 1 more electron. It was having 3 electrons, now it has 4 electrons, so it becomes negatively charged. So these charges are developed, and when charges are there, when they are moving, electricity comes into play. So that is frictional electricity. Now, here comes our second concept. That is conservation of electricity. Now, when we talk about conservation of charges specifically, we say that the charges are never, created or not destroyed. They remain same in a system. Now, let's, get back to the same example. Consider the case 1, where I have 2 electrons over here, 3 electrons over here. How many are total? Yeah, simple. There are 5, right? Now let's come to the second case, when the transfer of electron has took place. So it has only 1 electron, as it has given us 1 electron to this, who gained 4 electrons now. Now it has 4, it has 1. What is the total number of charges here? Again 5, right? So that is crazy. Now this is just a simple example to explain you the conservation of charges. Now there are many these charges in a particular system. You see the system of 2 surfaces always remains same. Great. Now we have come so far, and now we are going to deal with the crux of this chapter, the very basic law, that is Coulomb's law, which we are going to deal right at once. Great. Now we are going to deal with Coulomb's law. So, what is Coulomb's law? I'm going to say it and I'm going to depict it in a very simple way. So, the Coulomb's law says that the electrostatic force of attraction or repulsion between 2 point charges, yes, between 2 point charges is directly proportional. So let's say the electrostatic force is F. Okay, now this F is directly proportional to, as per the Coulomb's law, it's directly proportional to product of the magnitude of 2 charges. Now just say I have 2 charges, Q1 and Q2. So the product of magnitude of 2 charges is Q1 and Q2. Am I right? It's the product of magnitude of 2 charges, and this force is inversely proportional to the square of distance between them. Say these 2 charges are separated by a distance r. So what would be the square of it? Simple. That's r square, right? So Coulomb's law can be depicted in this format. Force, that is electrostatic force, is directly proportional to Q1, Q2 upon r square. Simple indeed. But when you come towards such statement, it's not just any charge, rather it's point charges, right? It is point charges. But what is point charge? Is it a charge with a point? Oh no, what is point charge? I'll tell you. Point charge is simply a charge which is of point size. That sounds crazy, doesn't that? Suppose say this is a charge and this is a charge. They're of point size, so they're called as point charge. But then what if I say you that even Earth or a charge of size of Earth can be a point charge? Now that at times is really crazy. How that is possible? I'll tell you. The basic concept which comes into here is it's not a charge with just a point size. It can be a charge with Earth's size. But this charge will be called as point charge only if it is separated by a distance from another charge much longer than its diameter. Say a meter you see is 12,800. That is 12,800 kilometers, right? So the distance between these two charges should be much greater than this 12,800 kilometer. Then our Earth will also be, that is a charge of the size of Earth will also be called as a point charge. Are you clear with that? Great. So we'll deal with this Coulomb's law once again. That is, the electrostatic force between 2 point charges is directly proportional to the product of magnitude of 2 charges and inversely proportional to the square of distance between them. We write it in this format, but then, whenever we have to remove this proportionality, we have to bring into a constant. Okay, so I'll deal with that. So force is equals to, say my constant is C, Q1, Q2 upon R square. Great. Now you know what? The scientists have struggled long and they got the value of this constant C, which will always remain constant, also a constant. A basic one. So C is equals to 1 upon 4 pi epsilon naught. Hey, wait, but what is epsilon naught? Do you know that? So let's deal with that. So here we have come to a point where we are meant to study not just epsilon naught, but also epsilon and dielectric constant. So let's deal with that. What is dielectric constant? It's the ratio of epsilon and epsilon naught. But what are these two concepts? Well, very simple. Let's deal with that. Epsilon is permittivity of medium and epsilon naught is permittivity of vacuum. Hey, that is going really confusing. What is permittivity? Okay, let me tell you friends, don't worry. It's very simple. Permittivity is simply the ability of a medium to store energy. Okay, in the electric field, yeah, that comes into a point in the electric field. So say, now we'll deal with a very basic example to get clear with that concept. Say I have a box. This box has ability to store, say, 10 mangoes, okay, 10 mangoes, and say I take a bigger box. It has an ability to store 25 mangoes. So what is this? Similarly, every medium you see, be it air, be it vacuum, or be it any other medium, they have ability. But not the ability to store mango over here, but the ability to store energy. Okay, so every medium has an ability to store energy, but in the electric field, whenever a point charge comes into a medium, so electric field is being generated, and because of that electric field, every medium possesses energy to be stored by, and that is called as permittivity. So when it comes to medium rather than vacuum, it is epsilon, it is called as epsilon, and when it comes to vacuum, or also I can say air, so it is epsilon naught. Clear? In terms of vacuum, it is epsilon naught. Other times it is epsilon. Now what is K? K is dielectric constant. Now this sounds a heavy term, but it's simple. It's just the ratio of epsilon upon epsilon naught. Simple. Now we come to a point over here. So you are clear with this constant, right? 1 upon 4 by epsilon naught. Its value you see is 9 into 10 raised to 9. Okay, Newton meter square per Coulomb square. Now this is as per the conversion factors. So here we come to a point. So what is actually Coulomb's law? It's nothing. That force is directly proportional to the magnitude of charges and inversely proportional to the square of distance between them. Very similar to the gravitational law, right? So it is nothing but the extent of force being exerted onto unlike charges or like charges. And that is what Coulomb's law. Meet you in the next lecture. Thank you.